Picture a sealed cooler full of ice and drinks sitting on black asphalt in the middle of a July heatwave. Our intuition immediately tells us what's going to happen. The ambient air is hotter than the insulated interior, so the temperature inside that cooler is going to rise. But knowing a general trend isn't the same as making a precise measurement. If you need to know exactly when that ice turns to water, intuition won't provide a timestamp. Observing present conditions is easy. To predict a specific future, we have to build a rigorous mathematical bridge from right now to a time that hasn't happened yet. That bridge is built using differential equations. This is the language scientists use to write the basic laws of physics, chemistry, and biology. At its core, a differential equation defines a strict relationship between a changing quantity, like temperature or position, and its derivative, or its rate of change. It's a rule. It looks at the state of a system right now and dictates exactly where it will be one microscopic instant into the future. By chaining together an infinite series of these microscopic steps, you trace a continuous path forward in time. This process turns a localized snapshot of the present into a reliable trajectory, allowing us to use short-term information to determine a system's long-term behavior. So how do mathematicians actually map out these microscopic steps to see the big picture? They start with a first-order ordinary differential equation. This formula takes a specific time and position and outputs a single derivative, a precise slope. Because that formula works for any input, it provides a specific slope for every possible point in space and time. This creates a direction field, a visual map of the mathematical wind pushing across the graph. If you drop a point onto this map, it will trace a path by naturally following the wind of those arrows. We call this path a solution curve. The rules governing this space never change, but your starting position dictates your path. By shifting your initial value, you generate entirely distinct futures across the exact same field. A direction field translates raw algebra into a literal, visual map of every possible future state a system could experience. To pull exact answers, they rely on analytical formulas, visual direction fields, and step-by-step numerical methods. If we go back to our melting cooler, we can see how this looks in practice. Notice how this equation is grouped into two halves. The left side is the system. It contains the current internal temperature and the physical properties of the insulation. The right side is the signal, the external ambient heat forcing its way into the box. This specific structure allows us to mathematically isolate an object, letting us calculate exactly how it will respond as the outside world fluctuates around it. Of course, the real world rarely isolates things so cleanly. Variables in nature are constantly bleeding into one another. To handle that complexity, we use a first-order system. This is a setup where multiple equations are linked together, because the rate of change for one variable directly depends on the state of another. Think of a predator-prey dynamic. A deer population grows steadily until it is limited by wolves. Simultaneously, the wolf population can only grow if there are enough deer to sustain them. To model this, we take two distinct first-order equations and wire them together. Each equation feeds its output directly into the input of the other. By linking these simple instant-to-instant rules into a continuous feedback loop, we gain the power to model chaotic, deeply interwoven ecosystems. We can scale this logic up to the absolute limit, all the way to the most famous law in classical physics, Newton's force equals mass times acceleration. But acceleration is the rate of change of velocity, which is itself the rate of change of position. Because it deals with a derivative of a derivative, F equals ma is actually a second-order equation. Yet mathematicians have an elegant trick. By using a tool called a companion matrix, that second-order equation can be sliced directly in half, expanding into a system of two interacting first-order equations. By reducing higher-order laws to these simplest consolments, we find that first-order equations serve as the basic building blocks for almost every model of physical change. By breaking reality down and mastering the relationship between a single instant and the one following it, we can translate microscopic information into a clear understanding of the long-term behavior of the entire universe.